Okay. So let's go back to the weak form for elasticity. Just going to rewrite it. This was last Friday we covered this. So that's how we sort of ended last Friday's class, right? We gave some of those names: stiffness matrix, mass matrix, other things, right? Remember that this term plus u, well, this term times the unknown displacement u is the stress, right? So this is stress C, B, U, right? So remember, B is the strain displacement matrix, so that's a matrix of the derivatives of the shape functions, right? So we have the derivatives of the shape functions times the unknown displacements, that's U. I mean, that's strain, rather. That's strain, sort of like the derivative of U. And then we multiply by the elastic constants, and then we get stress. Okay. So we could write the integrand up there as B transpose times stress, B transpose times sigma. And in fact, we have to if we're not doing elasticity problems. Right? If we have plasticity, it's a little bit more complicated than just CB. Right? So a lot of times you'll just see B transpose times the stress in the integrand. So, and the way, using all this notation, these are vectors, right? This is B and C are matrices. So the stress is a vector, and it's a vector, remember what it'll result in. Since this is plane elasticity, it's like sigma xx, sigma yy, sigma xy. Right? But in 3D and in general, if you remember when we introduced that Voigt notation before, we had like sigma xx, sigma yy, sigma zz, sigma xz, sigma yz, sigma xz, sigma xy, right? So that's going back to when we use the Voigt notation in the continuum, right? We covered elasticity in the continuum. Okay, so we also talked about, when we talked about poroelasticity, we talked about an effective stress, right? And we said that like the total stress is the effective stress minus the BO coefficient. We did it in additional notation, so we had like sigma ij, delta ij times the pressure, pore pressure, right? But we could also write this in sort of this vectorized notation. If we just introduce one new thing, we say, okay, so the stress vector is equal to the effective stress vector minus, minus MP, where M is 1, 1, 1, 0, 0, 0 in 3D, and 1, 1, 0 in 2D in plane elasticity. Right. So this is sort of the vector version of the identity matrix, or it's consistent with consistent with the Kronecker delta in the role it plays, right? In that we only want the pressure to apply to the isotropic components of the stress, right? So we only want the pressure to act on these terms, right? So it plays the same role. So now we want to develop a finite, yeah.
So you said if you are giving plasticity, then it has to be in terms of stress. But I mean, does it work if it was in terms of strain itself? Because the strain are the important thing in plasticity, right? Like BU, or does it have to be stress?
Well, we're going to cover this. We're going to solve a plasticity problem, computationally, but BU is the elastic strain, right? But remember, we decomposed the strain. So then we said that the total strain is the elastic plus the plastic part, okay? So what we can do is we can say that you can rearrange that equation, and you could say that the elastic strain is the total strain minus the plastic strain, and you could plug it in right there. But then you have to solve for the plastic strain via return algorithm, right? So, yeah, I mean, if you really wanted to write, I mean, you could say do a decomposition, I guess, on the displacements themselves, and you'd have like an elastic and a plastic displacement. So then if you plug that in, you'd have an elastic and a plastic. Well, you'd have BU minus BU plastic, right? That would be the elastic. So, but we don't really typically, there's nothing wrong with that. It's the same thing. Like BU is the strain, right? So, but you don't typically see that notation. Usually when you're talking about nonlinear problems, finite deformation, you just see B transpose times the stress in that term. Okay, so on the next slide, we're going to write down the finite element formulation for the poroelasticity equations that we derived earlier in the class. But there is one caveat in that the pressure, okay, so I wrote down the elasticity equation, and you'll see that it's only slightly modified, right, by just saying the only thing we need to fix the momentum equation is to include this term and that guy, right? Because that's plane elasticity. If we just have this in that thing, then we have the conservation of momentum equation. But we need to interpolate the pressure. Pressure is unknown, okay? And we need to interpolate the pressure. So we're going to say that the pressure is approximately defined by NJP PJ. So the PJs are the unknown pressures, and NJP, excuse me. I've coughed for a couple weeks. Anyway, these shape functions, I'm going to put the P superscript on them because they're not necessarily the same as the shape functions that we're going to use to interpolate the displacements. And in fact, we'll see next time that for stable element formulations, they can't be the same. Okay? Meaning the same order. So we can't use linears to interpolate the pressure and linears to interpolate the displacement. So we'll see why next time. But that's why we're going to include the extra.
Does the rule change also? Like if you have a fluid, because I mean if you have a fluid, so U changes, as we said, so the sigma changes. But then what happens to rho in the second and third term? Because rho could be the rule of solid.
If you remember, yeah, that's just the row of the solid.
Would it be the rule of solid?
Well, it's actually of the mixture, right? If you remember from the equations, it's the density of the solid plus the fluid. Right? Yeah. So I'm not carrying all those superscripts around that I was previously, but. So I'm just going to write down the equation. I mean, we know the process at this point, right? It's just math at this point. We multiply by its test function, integrate over the body, integrate by parts, all that stuff, right? So with this pressure here, I don't want to confuse you, but I put a vector symbol on it. It's a vector of the unknown pressures at the nodes, right? But pressure is clearly not a vector. Pressure is a scalar quantity. But since, over that element, depending on the order of interpolation, say if we use linear interpolation over a quad 4 in NP, then that in the thing in the brackets is going to be a 4 by 4 matrix. And the pressure vector will be the 4 unknowns. So now I'm going to add the U superscript to the shape functions here. Of course, that's implicit in the B's, right? The B's are the derivatives of the U shape functions. So that's the momentum equation. Then here is the conservation of mass equation. recall that M is or rather 1 over M. M is the BO modulus. 1 over M or something like that. Oh, I keep turning my thing off. So that's the equations of poroelasticity. Now, if we give these guys some names, this is our regular old stiffness matrix. We'll call this Q matrix. I'm going to call this M tilde, just to not confuse it with the BO modulus. But it's like the mass matrix. It is the mass matrix. And these are your external forces. I'm just going to call them the force 1, right? So these are your body forces applied to the solid times any external tractions. Notice this is just Q. We'll call this H. We'll call this S. And this we'll call F2. So that's your flux in and out and your diffusive the Q, yeah, accumulation, right? Accumulation. All right, so with those definitions, we can write this whole thing a little more compactly. So that's in matrix form. So the zeros are understood to be block matrices on the left and vectors on the right, to make everything consistent.